Okay, so before we start, could you all check that you are in the working directory of your R project? So is this the directory that corresponds to the project that we created at the very beginning? And if that's the case, then inside that directory, you should have a data directory, capital D, lowercase d, with this data that you got on the drawings. Yes? No? Thank you. So those that are in the expected directory, could you put your green sticky notes up so that we know, so that I know that we're all ready to go? I just want to make sure that we are all working together. Okay, so before talking about correlation and linear regression, I think we need to start with a word of caution. And actually, every lesson about statistics, machine learning, anything related to data analysis should always start with a word of caution. And this word of caution will be illustrated with a very famous data set, the Anscombe data set. That is, it's already in R. It comes for free with R. And so these are 4 pairs of values, x1, y1, x2, y2, and so on. They look okay. There's they aren't any missing values, which is already a good thing, and they look okay. So the kind of statistics, descriptive statistics that we could calculate with any new data is, for example, the mean. So how could I calculate the mean of my first column? Anyone? Yes? Sorry, so I didn't hear the beginning. Mean, okay. Oops. Mean. Bracket. Sorry, do you mean parentheses or bracket? We'll see. One comma. Comma 1. Yeah, if anything, it would be comma 1 because we want a column. Anyone else? A suggestion? Yes? Okay. So, sorry, mean. After mean? Like this? $x1? Okay. Yeah. So you have mean, which is a function. So the function call always requires a parenthesis. And the square bracket operator comes from the subsetting of a data frame, like this, with 1 for the first column. Yes. Okay. And so how can I calculate the mean of the second column? Anyone? It is not a difficult question. There is no trick. Yes. I push my up arrow and I change the 1 in 2. Oh, it's 9, 2. That's interesting. How can I calculate the mean of my third column? So you get to, a quality of somebody that programs is laziness, a good quality. So I'm going to do something. I'm going to create a variable I, and I'm going to set it to 3. Okay? And now what I'm going to do is that I'm going to say I want to calculate the mean of the ith column. Okay? It's 9, 2. There is a pattern. And now I want to calculate the mean of my 4th column. What I'm going to do is that I'm going to change the value of I, going to make it 4, and I'm going to call the same. Let me write this down here. I is 4, and I want to call means, it's going to be I. What is wrong? Mean. Here. So 9 again, interesting. But do you see something interesting here, right? I know I'm going to do the same thing over again. The only thing that is going to change is the position, is the index of the column. And all the rest in this piece of code is going to be exactly the same. When you have that kind of thing happening, that kind of event, when you get used to programming, this will immediately trigger a red light in your mind, and the red light says iteration. You repeat, you do the same thing over and over again. And whenever you iterate, you do the same thing over, well, not exactly the same thing. There is this I value that changes. That's when you want to write loops. So we have seen loops before. The for loop. Where we could say for I in 1 to 4. So every time, so 1 column 4 means 1, 2, 3, 4. So every time we go through this loop, I will get the new value, the next in line. The first time we run it, I will be 1. The second time we run it, I will be 2, and so on, and so on. Okay, we can try this out. I just need to add a print statement here, otherwise I won't see anything. So the first 9 corresponds to I equals 1, I equals 2, I equals 3, and so on. But really, I don't want to have I equals 4. I would really like to have from 1 to 8. And so here's what we see. The mean of the x1 is 9, x2 is 9, x3 is 9, x4 is 9. And the mean of all my y's is 7.5. That's an interesting property of a data set that we would not have guessed by just looking at the data. And actually, I'm just going to change this code into an as apply. Into an apply 1 to 4, or 1 to 8. This is another way that you also saw earlier to do iteration. Okay. It's another way to write a for loop, and it means the following. So what do we want to do many, many times? Sorry, yeah. Sorry. Here. I'm confusing myself. So what I want to iterate over what data? The data is this data frame. So I have the data frame. Let me print it here on the left. And so I want to do something systematically over that data frame. Do I want to do this thing systematically over the rows or over the columns? This thing that I want to do systematically is a mean. Columns, yes. In R, what is the first dimension? What is the second dimension? What have we seen so far in square bracket operators? What comes first? Rows. What comes second? Yes. And I have a mistake because I want to iterate over the columns, so I need to put a 2 there and not a 1. If I wrote 1, it means do something over the rows, but I want it over the columns, so I put a 2. And what do I want to do? Calculate the mean. So that's a pattern that you will see very often in R, is these apply functions. Apply something over the dimensions of a data frame. And here we go, the means for x1 to y4. Let's try to calculate the median. So I change here mean to median. And here we go. Let me run it again. 999. Open here, we have 8. That's strange. Oh, okay, not the median. I'm confused. It's not the median. The median changes, but it's the, what did I put in my? The variance, yes. Okay. So you look at, if I look at my variance, not the median, my fault, the variance is also the same for all my x's and all my y's. Okay. And actually, I'm going to show it here. The correlation, I'm going to show it here because otherwise it would involve writing a code that we haven't seen. But if I look at the correlations of xy, x1, y1, x2, y2, x3, y3, x4, y4, they all have the same correlation too. So very interesting properties here from a relatively small data set, and there is no way we could have spotted these just by looking at the data. But, and so here we see the same correlation. This one is actually the most interesting one. The same correlation. But when we try to plot this data, I'm just going to show you how we could plot it. Plot, and it's going to be 1, and this would be 5, right? Because I want to plot x1, y1. Yes. Let's try again. Here we go. So this is how I would plot it. I extract column 1, which is x1, and column 5, which is y1, and here I get it. This is what I get for my first pair. And I could repeat that for 2 and 6, and so on. Actually, as we talk a little bit about iterations, if I put I equals 1, I could put I here. And what would I put here? Anyone has an I plus 4. And so if I wanted to plot the second pair, here we go. Okay, so again, here is a specific pattern. So if I wanted to create these 4 plots in one go, I would iterate over values 1, 2, 4 for I, and always call this same piece of code here. So if we plot these 6, this is what we get. Anyone has an opinion about these 4 plots? And actually, these lines that we have here are the linear regressions of these, is it 10 by 10 pairs of points. So has anyone a comment to make about these data sets? They look, yes, that is true. Despite the fact that all the x's have the same mean, all the y's have the same mean, they have the same variance, and they have all the same correlation. But actually, there is only one of these pairs where doing a linear regression makes sense. Okay? The first one. All the other ones doing this analysis is wrong. It's not that it's not good, it's that it's plainly, simply wrong. This is not a linear regression. Oh, sorry, a linear relation. Okay, so what we are computing there does not make sense. Here we have a linear relation for all but this point. So actually, and these are perfectly aligned, but because of this outlier, what we do here is wrong. Okay? So we do this mistake because we didn't look at our data before doing our analysis. Same thing here, definitely no linear relation. Well, actually, yeah. Linear relation would be like this. Okay, so x does not vary for all the values of y, but because of this outlier, we get the same correlation. So, if we want to calculate correlations, if we want to calculate linear regressions in our data, the first thing we need to do is to look at the data and make sure it makes sense. Oh, and actually, on Wednesday, I think, or Tuesday, there was this new data that was published that is Anscombe, but pushed a little bit further. All these data sets have the same mean for x, y, standard deviation x, y, and the same correlation. Okay. Anscombe data is really old, and that's kind of brand new. It's pretty impressive. Okay. So let's see how we can calculate correlations. And to do that, we are going to load a data set that is provided for you. And it's called IPRG2. And it is, in my case, in my data directory. Oops. Okay. Could you load that data? And tell me what class it is and what dimensions it has. Once you're ready to tell me, could you put your yellow sticky note or green sticky note up, please? And I will choose a volunteer to tell me what class it is and what dimensions it has. So do you all have this IPRG2.RDA file? If you type load, if you type this, load, the name of the directory, some people have data with a capital D and then IPRG2.RDA. If you type this, does anything red appear? Yes? You have, a red means an error, that's not good. Have you loaded the data? I'm sorry, I thought you were, I thought you were looking at me and saying yes. So you have loaded the data. Good. Does anyone want any help with loading the data? Okay. So a volunteer. What is the class of the data? Yes, sir. Oh, 1 second. Just okay. It's a data frame. A data frame. Very good. And somebody else. What are the dimensions? I have no idea. Let's check. I know it's a data frame. It sounds about right. IPRG2. Yes. Has anyone looked at the data? Can anyone tell me what it is? Pardon? The intensity different profiles for each point. Yes. So it's the IPRG data, but it is a bit different. In what respect is it different than the IPRG data that we looked at so far? So let's look at names, IPRG. So these are the 12 columns. And these actually correspond to the RONs. And if I look at row names, IPRG2, these corresponds to all the proteins. So actually this is the same data set, but in the wide format. Before that we had long format, where we had all the RONs, all the conditions, and one column for intensity, or log2 intensity, and then proteins repeated as many times as needed. Each protein was actually repeated 12 times because it had 12 RONs. This data has been converted into the wide format. So proteins along the rows are repeated only once, and for each row we have the 12 intensities of that protein across all the RONs. And if you want to see how it was converted, it's shown here with a package, another package called tidyr, and it has a function spread. Okay, and there is a function melt too, where we can transform long data into wide data. And so on. Okay, the only thing is that I also removed, I used the first column here to set the row names. I don't know if you remember here in hat IPRG, which I do not have anymore. Okay, in hat, this is IPRG. The row names, IPRG, were not useful. These were just the indices. Okay, not really useful. But now in the case of IPRG2, the names become useful. Because the row names are proteins. So now I could use a protein name, and I'm not going to type this because it's too difficult to type. I'm just going to copy it. Okay. So now IPRG2, how do I copy on the Mac? Oh, not like that. Yeah, but it's not control, it's this other key. Ah, yeah, okay. Control C. V, okay. Here. Okay. So the name of protein quoted. Now suddenly the row names become really useful, where not before, because now a row corresponds to one protein. So it's the same data set, but formatted differently, which for this particular application is more useful. Oh, and another thing that we're going to do is to simplify it, to make it a little bit smaller, because very often, when you stop your analysis, eventually we will want to do this, what we do for all the samples, all the RONs. But when you start, it's always good to start with a small subset of your data set and something where you have some expectations. So my expectations here, I will try to verify them or to look at this by taking a subset, and what I suggest is 1, 2, and 10. Okay? So we're going to take columns 1, 2, and 10, the first, the second, and the 10th RON. And I'm just going to call this, I'm going to call this X. Okay? So I create this temporary IPRG2, sorry. So I create this temporary variable X. X is short to type, but it's temporary. I'm not expecting to save it, store it. It's just now to have a play around. Okay. And why did I choose 1, 2, and 10? Because 1 and 2 here correspond to technical replicates A and B of condition 1. Here's sample 1. Somehow the RONs were called sample 1, 2, 3, but actually sample 1 is condition 1. And number 10 is technical replicate A, but for sample 4. condition 4. So when I start to look at the correlation between, and I look at these data, I expect these two to have a better correlation than with this one. This is why I take 1, 2, and 10, technical replicates of the same condition, and this is a different condition. And so the first thing I'm going to do is to use a new function, but that is very useful. I think you'll like it, because it'll do many things for very little typing. It's the function pairs. And pairs, does the following. Do you like it? It takes all my columns of my data frame. That's column 1, 2, 3, and it will do all the scatter plots for me. Okay? So my first column is row, second row, third row, or first, second, 10th actually, and that always produces the scatter plots, which actually corresponds to repeating multiple times x1, x2, which will produce the plot there, x1, x3 produces the plot there, and so on. So it's quite handy. But again, this works for small data set. If I tried this with the full IPRG2 data set with 12 values, it would not be useful. I will just get tons of scatter plots. Too many to look at. Okay. And so the first thing we want to learn about is the correlation. How can we calculate the correlation of two variables? I should not have deleted this. Too late. So x1 and x2. If I want to calculate the correlation, is that? Yeah, I think it's going to work. Of these two, I can use the core function, where my first input, my first argument is the first vector of values I want to calculate the correlation of with the second. Okay, so I want to calculate the correlation of my first row to my second row, the correlation of these points. Now let's see if that works. It does not work. Why does it not work? Anyone an idea? Okay, let's see. Can I calculate the correlation of 1 and 3? No. 2 and 3? No. So why does it not work? Anyone? Do you remember the example that we had? I think it was, I don't know if it was Wednesday or Thursday, with the mean. Mean C1, 2, 3. So whenever you have NAs, you do a computation, you have NAs, immediately you must ask yourself, do I have any NAs in my data? And so instead of calculating all these correlations one by one, the core function can also calculate all the correlations. If you give it a data frame or a matrix, it will calculate all the correlations between all the columns. Okay? So the correlation between my first row and my first row is 1, and the correlations between all the, and that's diagonal, 2, 2, and 3, 3, they are 1, but I can't manage to calculate the correlation for the other ones. Why? Most likely because I have missing values in my data. Now, did we have any missing values, any NAs in IPRG, the data sets that we used yesterday and in the morning? Did we have any missing values? Did we flag these? Did we realize we had any missing values? Yes? I don't think so. Well, let's check. And we can check this with a function called NA, IPRG false. There are no missing values in IPRG2. IPRG. If we look at X, are there any NAs? Yes. I have missing values in X, which is a subset of IPRG2, which was created from IPRG. Why is that? Can anyone figure out why? The only thing I did was I had this long format and I made it wide. Why do I suddenly have missing values? Yeah, that is a good point. I have missing values because no missing values means that all proteins have been observed in all samples. Imagine that I have proteins 1, 2, 3, or let's just say 1 and 2. Okay, for my ROM 1, 2, sorry, 1, okay, and I have 2 ROMs. So I have protein 1, 2 that is repeated, and here I have my intensity. I1, I2, I1. Now imagine I do not have any, I have a missing value here. Well, actually, if I have a missing value there, that row is not even present in my long data. But when I convert this into a wide data, I look at how many proteins do I have? P1, P2. How many RONs do I have? RON 1, RON 2. And now I fill in the intensities. I11, I21, I12, and there is nothing to fill there. So I have a missing value that appears in my wide data. Is that a good thing or a bad thing? Any either? Yeah, I don't know. Well, actually, I like it. I like it because it makes it explicit that I have not measured all the proteins in all the samples. In this particular case, I find it useful. You know, it's an important property of my data, whether I have missing values or not. And this is something that I would like to be able to discover very, very quickly. It would not be straightforward to identify in this IPRG dataset, the first one we have in the long run. So that is one reason I think that the wide format is useful sometimes. Actually, also for the pairs. Calling this pairs function here works by taking all the columns. That would not be possible with the long format. But there are many other really, really good reasons to, for the long format. Okay, so now we have identified why calling the correlation here does not work. So what can we do to fix that? What have we done previously when we had missing values? Yeah, we removed the NAs, and the functions that we use, there are different ways, or different ways to do it, but we used one of the functions, one of the ways that we saw was to use na.omit. And actually, before doing that, we should look at the documentation of the correlation. Right? Let's see if core does not have an argument that says na.rm. Mean, median, they all have it. But core does not have it. It has an x, y, use, method. Oh, maybe use actually. Maybe use, let's see. Use. Complete ops. Okay. So core has a way to only take into account complete observations. I didn't know that. Typically, they are called na.rm. I'll just carry on the way I did it in the notes. Wrong screen. Wrong screen, where I just created a new temporary variable that I called x2, which is like x minus all the rows that have a missing value. And here are the correlations that I calculate, calling core x2. And I increase change this to make it more readable. Maybe that. Okay. So if I look at the correlation between my first sample and my second, my first and my second row, sample 1 replicate B and A, I have a correlation of 0.97. When I look at the correlation between replicate A of sample 1 and replicate A of sample 4, I have a 0.95. If I look at the correlation between last one, which is condition 4, replicate A, 0.95. Here they are, the two other ones. Condition 4 and condition 1. Okay. So indeed, these are smaller than the correlation within the same condition. Okay. So I could calculate this same correlation now for IPRG2, which would produce a much bigger, I still have my missing values, but which would produce a much bigger correlation matrix with all the possible correlations. But another word of caution about correlations. Very often people think that correlation is a hallmark of replication. And actually that's not entirely correct. Correlation is more a measure of the order of the values that we measured. Not really a measurement of the replication. We measure something once, we measure it again. How close are these two? Really, if we want to look at replication of our experiments, it would be much better to look at the fold change of our measurements. A big fold change means that I measured something once and twice, and actually the measurements I have are far away. Okay. If I measure it 2 times and I get very similar values, I will get a small fold change. Okay. So fold changes typically are a much better way to estimate how replicable, the replicability of your experiments, not the correlation. And actually, when we want to look at the replicability and the log fold changes of 2 experiments, there is a really nice way to visualize that data with MA plots. Does anyone know MA plots? Okay. MA, very confusingly, stands for microarrays, because these plots were first kind of developed for microarrays, but you can do it with anything. It doesn't have to be microarrays. And so let me show you. Here is an MA plot for sample, so columns 1 and 2. So what is an MA plot? On the y-axis, I have the log2 fold change of my intensities. And on the x-axis, I have the average expression for these proteins. Okay? So I can calculate this as shown here. My replicate 1 is the first column. My replicate 2 is my second column. So these are log intensities. How do I calculate the fold change? I subtract these values. Don't forget, R is kind of vectorized. So if I subtract R1 minus R2, so these are the 2 columns. What is it? 3,600 values minus 3,600 values. What I do is that I subtract the first intensity of R1 with the first intensity of R2, the second intensity of R1 with the second intensity of R2, and so on. So in this one operation, I get 3,600 fold changes. And what I also do is I calculate the mean log2 intensity, again, for replicate 1 and replicate 2. And then I plot them, log fold change, and mean intensity. And so proteins that have not been measured reproducibly are those that point at the top or at the very bottom of my MA plot. Okay? Because I have big or small fold changes. But there is another very interesting pattern that we see we don't just look at the fold change. We could do a box plot for that. What we look is the fold change and the mean intensity. And what we see here, where is most of the variability in my measurements? Where is it? On the left. What is on the left? Yes, proteins that on average have a lower abundance. So of course, if I have a protein if I had a protein that in one measurement, in one replicate, was very, very low, and a protein that on the other replicate was very, very high, it would be here, and it would have a big fold change. So this happens, but it's very, very rare to find proteins that are highly abundant in one replicate and highly abundant in the other replicate and have a big fold change. So we have bigger discrepancies for low abundant proteins because we are much closer to the signal to noise ratio. So if we want to look at replication of our experiments, producing MA plots are actually much, much more informative than doing scatter plots. And looking at the distribution of our fold changes is much more informative than looking at the correlation. That doesn't mean the correlation is not useful, but we need to be careful, not make claims, and that's something that you read really, really often, that says, oh, we have high correlation, so we have good replication of our data. Of course, good replication of the data will lend itself to high correlation, but it's not, technically speaking. Maybe, I don't know, I don't think I'm a bit pedantic here, but correlation, replication, look at the fold changes. And here I just, this is the same MA plot. This one is done manually by calling plot. So you see, plot A for the x-axis and M for the y-axis. Does that make sense? And grid here just adds this nice little grid. And if I use another package called AFI, it has a function MA.plot, it will create this automatically, and then it does a regression for a plot. Okay, so MA plot, very interesting. Any questions? So I'm going to create these two variables here, R1, which is my first, and R2, which is my second replicate. Okay. And so I'm focusing on technical replicate A and B of condition 1. So now let me plot R1, R2. Okay, so it's here. And let me add a diagonal line that crosses the origin, 0, 0 of my plot. Okay, we don't see it here because there's no value. And has a slope of 1. Okay, that's a perfect diagonal. A grid adds the grid on my figure, and so I see here that 22, 22, 24, 24. Okay, and so this diagonal line goes through these exactly through the grid. But now, what I would like to do is to add not just this diagonal line, but to this figure, I would like to add the diagonal line that models these two continuous values, the measurement of my proteins in replicate 1, measurement of my protein in replicate 2. The linear regression of these two vectors. And before being able to plot it, I need to calculate it. And it happens to be something that is easy to do in R with the function lm. Okay, R2, R1. Oh, sorry. Okay, lm for linear model, and I want to model R2 as a function of R1. I'm going to store this result in a variable I'll call lmod. Yes, and the reason for this is that I need x2, because I don't want to have missing values. Wrong button. Just going to increase this. Here's my figure. Okay, it's essentially the same figure as I had before, except that there's probably, I know, it's the same figure. I thought maybe a dot would be missing, a protein, but I think I have missing values in replicate 1 and 2. So, and so let me calculate L mod, and I'm just going for a second to not look at the figure and look at summary of L mod. Here we go. So I believe you have seen the kind of theory behind linear regression with Olga. Is that correct? So here then we have our residuals, and the summary statistics of our residuals. We have our intercept and slope, and we have our R squared. It's 0.9594. Okay, so this is, if you want, the same type of output that we had when we did a t-test. Okay? It kind of tells us the usual things we want to know when we do a linear regression. Here it is. Just as for the t-test, it tells us the usual things we want to know when we do a t-test. And along the same lines as for the t-test, if we look at the names of this thing, this thing, this class, contains the coefficients, the residuals, and everything that we could go and extract if we needed them. If we just want to look at them, then we can type summary, and it gives us a summary of what we calculated and a summary of all the statistics. Okay? And actually, let me class LMOD. This LMOD object is not a data frame, it's not a vector, it's not a matrix. It's this special class called LM. And a class is something that, as a programmer, you can define. It's a new type of object that you can define. That's what they learn on the other side in the more advanced R programming, where you can learn object-oriented programming in R. And you can define these abstract classes that will model exactly what you want, okay, what is of interest to you. And when you want to do linear modeling, all this data, and when I say all this data, I mean these 12 bits of information are put together in a class, in an object of class LM. When you did a t-test, all the results, all the little bits that are of interest when you do a t-test were put together in an object of class, what was the class again? Or was it t-test? No, I don't think. T.test. It is of class h-test, not t-test. And why not t-test? It's because h-test stores the result of any type of, I'm very tired, sorry. The H stands for, help me, hypothesis testing, yes, exactly. Right. And so when you'll start to learn about new data, new packages, new functions, sometimes these will do complex calculations, and they might not just return one value, because if they do complex calculations, they will calculate many things, and they don't just want to return one thing. Like if you do a t-test, just returning the p-value would be really bad, because we know that the p-value can have issues. You can't just rely on the p-value. You want to look into it. What's the confidence interval? So t-test, you return many things. So when you start using R packages and bioconductor packages, and I trust you will find more and more cases where a function returns something that is more complex, that cannot just be stored in a vector or a data frame or matrix. And so one way to kind of start to understand what is this thing, or just how is it named, class of the thing, and it tells you that's the class. All right, but that's this digression. We calculate the linear relationship between R2 and R1. Here it is. And now what we want to do is to add this diagonal line. Okay? Before that, we added the diagonal line that had intercept 0 and slope 1 with this line. Plot. You know what? Let me add it, but with col equals red. Okay. This line, intercept 0, slope 1. But what we really want is the linear regression, which has intercept 0.35 and slope 0.99. And to do that, we can use AB line, the same function as we used there, but as input, we give it the result of our linear regression. An AB line will check what is this thing that I get as input. Oh, it's of class LM. I know LM. I know that if I get an object of class LM, I can go and look somewhere to get the intercept and somewhere else to get the slope. We can figure out where to find them, but actually as users we don't need to care too much. We just need to know that LM stores this information and AB line knows where to find it. So here I'm just going to use as another color blue. Okay. So very, they don't quite overlap. So the red one is 0, 1, and the blue one is our linear regression. Now we have these two replicates have a really, really good correlation. So indeed we expect that the linear regression matches the cloud really, really well. It's very tight. Okay? But there is another important aspect of linear regression that leads back to what we saw in the beginning is, you know, whenever we calculate something, it's important to look at it. Not just trust these numbers, take them for granted. And not just trusting the result of a linear regression means plotting and looking at the result of this linear regression. So now, here I think we can trust that, you know, it makes sense. We look at this data, it makes sense. But more generally, what you'll want to do is to plot LMOD. Again, plot is a special type of function that will adapt its behavior depending on what it gets as input. So now, plot will ask itself initially, what do I have as input? Is it a matrix? Is it a vector? No, it's an object of class LM. What do I do with an object of class LM? Well, somebody has written a specialized plot function that does the following thing, yes, with an object of class LM. It does different types of multiple plots. The first one is that it plots the fitted values and the residuals. And the theory tells us that these residuals should fluctuate around 0. It should actually be normally distributed around 0. Okay, so we expect that these residuals fluctuate here around 0. And those that are not as good as the other ones are highlighted here. The others that are far away, it's a little bit like an MA point. Okay, they are far away from 0. And they're actually also highlighted here. So these are the indices of these. Okay, here a plot of our theoretical and standardized, theoretical quantized and standardized residuals. Again, assuming that these data are normally distributed, we expect them to be along these lines, so that it's not perfectly. The outliers here are not, but they fit relatively well. Actually, most points are here. We don't see this because it becomes all black. Most points are here. If the data was not linear, was not to be modeled by linear regression at all, we would not have most of the points here. Okay. Next one, similar as we had before, the fitted value and the square root of our standardized residuals, and standardized residuals again, and the leverage, which is a measurement for each point that tells us to what extent does this point influence our linear regression. Okay. So points that would be really far away here and actually much further beyond these lines that we hardly see that do a similar type of measurement. So if they were really far away here, that would mean that these points are outliers in our data. And whether we take them away or put them in our data, they would dramatically influence the result of our linear regression. Do you, if you think back here in this data set, okay, these points dramatically influence the result of our linear regression. Okay. If we take this one away, we have all the points are perfectly on the line. Imagine we don't have this one, and we take that one away, it will not influence the regression at all. But this one influences a lot. So that one is a bad boy. That would be far away from this plot. So we need to look at the data. We have a scatter plot or these specialized plots that give us a way to inspect, to QC our results, and find out the bad boys and remove them. And the last thing I wanted to show you, and I'm going to show it here, is how to produce these figures. I'm always confused with my mouse. What way do I need to turn? Yeah. How to produce this same figure in ggplot2. Okay. So do you remember that plot is, we have seen plot with a vector. We have seen it with a data frame. We have seen plot with an object of class LM, where we produce all these fancy plots. ggplot is not like that. ggplot only takes a data frame as input. So if I want to produce this figure here with ggplot, where here I have a vector R1, a vector R2, intensities of proteins in the same order for replicate 1 and replicate 2. If I want to generate that figure with ggplot2, the first thing I need to do is to create a data frame. No data frame, no ggplot2. Okay? So here's what I do, data frame. Actually, I also added M and A already. But actually, strictly speaking, we don't need it for this one, but we'll need it for it. Okay. So here I create a data frame that has as many rows as I have proteins. The first column contains the intensities for protein 1. The second one contains the intensity for protein 2. The third one contains the fold changes. Sorry, what did I just say? That's nonsense. No. The first column contains the intensity of replicate 1. No, I said that. So it was not nonsense. And the second one contains the intensities for replicate 2, protein 1, protein 2. The third column contains the fold changes for all the proteins. So fold change for protein 1, fold change for protein 2, and so on. And the last one contains the average intensity for the proteins, protein 1, protein 2. You need to tell me if I talk nonsense. Or maybe it's too late. You just take it for granted. So, how do we construct a ggplot2 dataset? We start with the ggplot function that takes two pieces of information, my data, which is here, this data frame that I elegantly called DFR, which is a name that I very often use for data frames that I don't mean to store. It's kind of a temporary, an easy way to name a data frame. At least that's what I do. And I need to do my mapping with my aesthetic function here. And my mapping is, on the x-axis, I want to look at column R1, and the y-axis, column R2. And I store this in P, because I don't want to have to type this too often. So, and let me copy this and type it. Oh yes. Oh, sorry. So here and oh dear. Let's try right-click, copy, right-click, paste. Yes. And after doing this mapping, I want to visualize these with, yes, no. Sorry. And I have not created M and A in this. That was with my MA plots. Were here. So let me quickly create this. Copy. Paste. Here. Run. I don't know, my run button. And oh yes, and P. So this is what I create. This is the ggplot that I get from mapping X to R1, Y to R2, and representing this data as with geoms points, with my geometric object point. And here is where ggplot becomes really, really nice, because ggplot has a concept of data, which plot doesn't have. And the concept of data is that, well, I have this P object, P that contains all the information for my plot. And what I want to add to it is another geom where I want to smooth my data. And how do I want to do that? With a method named LM for linear model. So if I run this, look, it automatically adds the result of my linear modeling. I haven't done it explicitly. And of course, if I wanted to look at the results, the coefficient, sorry, the residuals, my intercept, my slope, then I would need to calculate it myself. But if I want just to plot the result of this linear regression, ggplot2 is really, really nice. And another nice summary method would be, let me align these like this. Geom, another one that can be very interesting is quantile. And I'm going to say that my color here should be red, so we see the difference. Please, system. Oh, okay. Quantile doesn't work because apparently I'm missing a package here. I'm not going to install it. I'm just going to show you here what it is. Sorry. Where geom quantile will add the quantiles, okay, kind of the spread here along this linear regression. What the spread is. Now, it is very, very tight because we have many, many points here along this linear regression. That's the point, right, of doing linear regression. Now, it doesn't look like that because they are big dots, opaque dots. So these ones kind of jump to the eye, but we have many, many points here, so it's really fun. So ggplot2 is really easy to create these graphics and adding statistical properties of the data with statistical geoms. Okay. So I have a last set of exercises for you, and I will, after updated teaching material, put the answers, because I know it's late, so put the answers so you can look at that. But the exercises do not require anything new that we have seen ever since, so my suggestion would be to use this RPRG2 data set and take two replicants, whichever you want. We took column 1, 2, and 10. But it would be to repeat this with another pair of replicants of your interest. Plot them, model and plot them, plot the scatter plot, and plot their linear relationship. We have already seen how to get RPRG2. The second exercise would be to take any pair of x and y's in Anscombe, create a linear model for any xy, pair of your choice, and visualize and check it. Okay? Produce these figures. And in particular, if you take anything but xy, x1, y1, you should see kind of, striking patterns here. x1, y1 is the only one that is amenable to linear modeling. All the other ones, it's plainly wrong. So 2 suggestions for exercises. I suggest maybe something like 10 minutes or so, 5 to 10 minutes. I know it's late, so even if you don't finish anything, but maybe you still have a little bit of energy to try, and then we'll wrap up by 5, sure. Yes. So it loads a package. That package, so it's not in our page. Oh, if you leave, there are certificates. Not so for people for who it's the last course, you have certificates. If you come back next, you get those. So yeah, it just tells you that it loads a package. Now, this package provides a function that's also available in Mix. We do not go into these kind of details, but it did exactly what so it tells you that it's smooth. You didn't specify the smoothing. Oh, no, you did. Oh, yeah. No, you didn't specify form. So it assumed that it's y as a function of x. And this is exactly what you want. This is typically what you want. Yeah. When you have finished, or if you have enough, put your green sticky note up. Yes. That's not warning, it tells you that. So you say, so it's super smooth. Oh, is it? Basically it tells you that it hasn't specified before how it is smooth by default. It said it expects 40 why, which is exactly what you want. It's exactly what you want. But it just tells you. It's not an error, just default. That's why. Afterwards. sample one, and that sample which is the wrong person that's yeah, well, sample one. So we have sample one A, sample B, sample one B, sample one B. These are technical references and condition one. And these are not these are one. Sample one is condition one, which is one. So, for example, when we start and you take sample 1 and sample 2, and you get technical sample, you should have time to take that. And similar time. And then you could do the same thing. Any technical sample 1 and any technical sample 2. And then you expect modules. This is what you expect. So you could exactly this way. Here are your technical and I had some you would have different presentations. Technical reference within or very assume the technical reference is smaller. Otherwise it's not and you also expect from technical reference like the technical reference is something that's big, and the class is small, something like wrong. But yes, something like that. That includes also any technical reference. There you can expect to see substantially bigger parameters than what yes. That one contains biological so generally should be so small that it doesn't really matter. Because if it's of the same order just one comment based on the question here. So we calculated these, and I think I can show it here. These correlations, okay? So correlation of 0.97 is really good. There is nothing to discuss. Correlation of 0.95 is good too. And some people will say, oh, we expect a correlation greater than 0.8. Right, this is a good correlation. Or we expect a correlation, within. So the discussion was technical replicates and biological replicates. Imagine we have this experimental result. Okay, we have sample A, sample 1, and sample 2. Okay, these are biological replicates, two different samples. And let's imagine that here I have a technical replicate A and B. A and B. Okay. Personally, if it was my experimental design, I would prefer to have 4 biological replicates. I would not invest my money in technical replicates. That would be my decision. But maybe this is a new mass spec. This is a new piece of kit, new technology, new kit, and you want to assess the technical and the biological variability. Okay? But unless you want to, your question is, what's the technical variability? I want to make sure that my technical variability is much smaller than my biological variability. I would do 4 biological variabilities. But let's assume there is this. So what could you do? You could create pairs, with these 4 factors of intensities. Okay? So what would you expect? A small correlation or a small distribution, because we look at replication. So small correlations or small spread of my fold changes inside here, and a similarly small range or small correlation within these technical replicates. And then I would also compare any technical replicate of sample 1 and any technical replicate of sample B. It doesn't matter where I compare AA or BB or AB or BA, it doesn't matter. Unless you have run AA together on the same day by the same person, but that would probably not. So you just take one, let's say B and A, and if I compare these 2, I would expect to have a bigger distribution of fold changes, or not a smaller correlation. And here, these 2 better correlations, I expect them to be similar. If these 2 are very different, like 0.97 or 0.99, 0.9, and this one, let's say I just put numbers. Okay, 0.8, 0.99, 0.90. This is weird. I expect the same kind of correlations within my technical replicates. Okay? This would be weird. Maybe one of my technical replicates here was messed up. But let's assume I have similar. Now, I didn't want to put numbers here. I didn't want to put numbers because I am always very skeptical of people that tell me, oh yes, we expect to have correlation higher than 0.9 for my technical replicates and around 0.8 for my biological replicates, because it's all relative. It depends on what biological variability you measure. I don't really care about the actual values. Now, of course, if I get 0.5 here, in trouble. Right? But it's not the absolute value. Let's not be focused on an absolute value. Let's not be focused on a p-value of 0.005 or 0.001. It doesn't matter. It's just arbitrary threshold. Don't take 0.5 p-value to say it's significant, because of course everybody will make fun of you. But the actual threshold, 0.05 or 0.049, there is no reason to say 0.05 is better. Same thing here, is it 0.8, 0.79, it doesn't matter. But we want to be able to order them in a way that makes sense with our experimental design. Okay, so the actual values, I don't know, 0.8, 0.9. What really matters is, do they reflect your experimental design? So the absolute value, it's how we order them. And does this reflect your experimental design? Whether we look at correlation or distribution of our fold changes or the scatter plots, do they reflect, or the MA plots, do they reflect our experimental design? That is what matters. Any other question? In the meantime, I have updated the material. I think I should have, unless I'm not online anymore. Ah, yeah, I'm not online anymore. So once I'm online again, I push the changes. Otherwise, are there any questions about the material in this of today, or any of the 2.5 days? Any questions? Good. So in the readme.html file that you got in the beginning, or on the equivalent on the GitHub repository, there is another link called additional. So in the meantime, I have this readme.html file. Online has changed. I have added a schedule and things like that. So it looks different than what you got in the beginning. But both have a link called link to more teaching material. And I'm going to do a bit of advertisement for my work. So if you like R, you will come across many other opportunities in R. And this teaching material, all this, what you see here, and I will add the the material for 2.5 days here, but this is a collection of quite a bit of teaching material that have been using throughout the years. So if you look for additional information, so there is also very advanced R programming there, but there is also more basic R, package development, and for example, there is also basic R here, and I think at the very bottom, statistics primer, not as good as what you have seen today, but for example here, I think this is specifically about visualization of quantitative proteomics data. I remember that. And here, this is a workshop that I did end of last year in South Africa. These guys had 2 days of proteomics and mass spectrometry R. That was kind of very intense, from raw data to quantitative data statistical analysis. So there is a lot of additional teaching material there, in case you are interested. So that's it. That's all I had to say. If you come up with other questions, don't hesitate to send me a little email. Or ask your questions on the Etherpad and still send me a little email, and then I'll answer them on the Etherpad so everybody can read them. Okay. So thank you very much for coming and staying to the end. And if you are going back home, wherever that is, have a good way back. Thank you. Thank you.